All right, this is an example lab question or lab calculation for your potato lab, your lab number 3, which had the different concentration of sucrose with your potato. So here I have an example, a very similar lab. Carrot slices are placed in a sodium chloride solution, and there's one, two, three, four, five, 6 different solutions for this example. They're at 30 degrees Celsius, and the placement of those carrots in those solutions at 30 degrees Celsius resulted in percent changes after 24 hours of mass. So this is mass change that we have right here. Okay, and you guys are going. That's why you guys did the mass beforehand, so you can get the mass after and then calculate the percent change. So the first thing that you're going to have to do is you're going to have to graph your findings so you are able to determine the concentration of your potato, but in this case, I need to graph this information to determine the sodium chloride concentration of the carrots. And then, once I've done that, then I can apply it to the water potential, or the solute potential equation, which is psi equals negative I CRT. Okay, so let's go ahead and do the graph real quick. You're going to need a full graph, a full 4-quadrant graph, even though you're only going to be using quadrants 2 and 4. Okay, so over here we're going to go ahead and say this is a positive percent change, and down here would be a negative percent change. I don't need to say percent twice. Right, and then on the x-axis is going to be your molarity, right, of sodium chloride. I just didn't put the sodium chloride part. So labeling the axes, we'll just go ahead and keep it simple. This will be plus 10, plus 20, plus 30, plus 40. Okay, and then minus 10, minus 20, minus 30, minus 40. Obviously, your scale will be different than mine, or maybe different. And then you have the molarity. Obviously, 0.0 would be at the crossing of the x and y axes. Then you have 0.2 molar, 0.4 molar, 0.6 molar, 0.8 molar, and 1.0 molar. So now that we have our axes labeled, let's go ahead and plot our data. So at 0 molar, it was 20%. So we'll go ahead and put that right there. At 10%, or sorry, at 0.2 molar, we had a 10% increase of mass. Okay. At 4 molar, it was negative 3%, which is going to be right here. Let's see here. 6 molar, negative 17, so negative 17 at 6 molar, roughly right about here. Of course, this isn't perfect, and yeah, you would be using a ruler. At 0.8 molar is negative 25, so roughly right about there. And then at 1 molar is negative 30. Okay, so as you can see, we can get a linear regression here, and I'll have to go at freehand because I can't use a ruler on a smartboard. So, okay, so I had to use a ruler because that drove me nuts. So there's our linear regression line. Now, what does this line mean, or what is this line going to tell us? Well, what it tells us is at this point right here, okay, this is going to represent the sodium chloride concentration of the carrot. Okay, when you guys do the potato, you're going to follow the same rules when graphing, and where it's going to cross the x-axis, that's going to represent your sucrose concentration of your 2 different potatoes. Okay, you can put them both on one graph. You do not have to put them on separate graphs. But either case, you should still have a nice clear line going across the x-axis. And then when that happens, this x-intercept, that is going to represent your concentration. Okay, so now looking at this, I would say that the sodium chloride concentration of the carrot is approximately 0.38 molar. So that's the molar concentration of the carrot. All right, so now that we have that information, we can apply it to the problem. or the equation itself, which is going to be psi of solute is equal to negative I times CRT. Now, again, you don't have C yet. You need to do the graph to find out what the concentration of your potatoes are. In this case, if you remember, my concentration for the potato, or for the carrot, was, let's see, carrot concentration was equal to 0.38 molar. Okay, R is equal to 0.0831. Now the unit here is very similar to the unit for the gas constant, because it still is the gas constant, but instead of liter, atmosphere, mole, Kelvin, like we learned in chemistry, it's liter, bar, mole, Kelvin. Okay, and actually I think there's only one R in bar. And then temperature is, again, because we have Kelvin right here, we need to make sure that our temperature is in Kelvin, which is a Celsius temperature plus 273. Our temperature in Celsius was 30 degrees, so our Kelvin is 303 Kelvin. Now I is the ionization constant. Okay, like it's just a factor based on what type of solid we're looking at. Now, in many cases, it's like I said, it's going to be 1 or it's going to be 2, depending on the if the substance that you are solute that you're looking at will ionize in the water, and if it does ionize, how many ions does it form? For example, if it's sucrose, sucrose does not ionize, so I would equal 1. Sodium chloride will actually break apart and ionize into sodium ions and chloride ions, and you'd have a an ionization constant of 2. If, for whatever reason, you wanted to do the, let's see here, the calcium phosphate ionization constant, okay, then you would have 1 calcium 2 plus ion, and you'd have 2 phosphate 3 minus ions, so you'd have an ionization constant of 3. Guaranteed, this is probably never, ever, ever going to be done, but I just wanted to show you that if you did, then that would be the ionization constant. Now, since for this carrot exercise, the solute was salt, sodium chloride, so we're going to use an ionization constant of 2. Okay, so let's lose this so we can do the math, and we plug in our answer, or plug in our numbers, so to speak. I'm trying to solve for psi of the solute, which means it's -2, okay, times the concentration. Remember, it's in molar, so it's 0.38 moles, okay, per liter, and then multiply that by our gas constant, which is 0.0831 liter bar mole Kelvin, and then multiply that by 303 Kelvin. Okay. Like I said, first thing you want to do is get rid of all of these units. Okay, Kelvin will cancel out, moles will cancel out, and liters will cancel out. That leaves us with bars, and that's the unit that we're going to have left. Okay, so when I do the math, I'm going to end up with like -19 point something, but I only have, in this case, I have 2 sig figs here, so it was like 19.3 something or 19.4 something, but because of sig figs, we're just going to go with -19 bars. Okay, and the question is, well, what does this mean? Why do I even care about that? What is water potential to begin with? Okay, water potential, like was mentioned, is the potential for water to flow towards a certain space. Okay, usually the lower the water potential, i.e., a very large negative number, water is going to want to flow toward it. Okay, and if I put these carrot cells, okay, in a solution of distilled water, that is, for example, the water potential of distilled water is equal to 0 bars, right? Well, if this is now, understand, let me backtrack real quick. This is 19 bars, that's the solute potential, but because there's, in many cases, especially in our lab, there is no pressure. So it's, if we were to do the experiment, we go, water potential is equal to the solute potential plus the pressure potential, right? But since the majority of the time that we do this in lab, pressure potential is going to be 0. So in essence, the water potential is equal to the solute potential for us. Say, and since I say that the solute potential is 19 bars, and since it was an open container that we did this in, I also say that the water potential, not just the solute potential, but the water potential for these carrots are also negative 19. And so what does that mean? That means if I have water available and I have a carrot cell available, which I don't have an orange pen, so we're going to have a blue carrot with the nucleus. Okay? Because because it was just a very, very low number, okay, negative 19 bars for their water potential, that means water is going to have the tendency to flow in to the carrot, which makes sense because that's why when you put a carrot seed into the ground, the carrot seed is going to have a lower water potential than the soil. Therefore, the water from the soil is going to go into the carrot cell, and then, 66 days later or whatever, you get a carrot. Okay. But this is just an example of what you guys are doing. You guys are going to use potatoes instead of carrots, or you use potatoes instead of carrots. And the other big difference is your temperature that you guys had in class was 25 degrees Celsius, not 30 degrees Celsius. So that temperature is going to change. Okay, R is going to be the same. I is going to be 1 because you guys use the solute of sucrose, which does not ionize. Therefore, the ionization constant is only 1. And then the concentration, you are actually do this equation twice, or this calculation twice, because you need to find out the concentration of both the sweet potato and the russet potato, and then based on the concentrations, get the water potential of each individual potato, and then based on that, decide which potato has a lower water potential. And what you can tell with that is, if I had a potato cell or a sweet potato cell or a sweet potato cell, in which direction would water more likely go? Okay, so that's an example problem for your osmosis lab. So if you have any questions, please ask.